Hello, everyone. Can you hear me?
Yes.
Okay, thanks. So I think we will start in 1 minute. So yes, so so we're going to have the last session with ATVA 2020. So I'm Zhening Wu, the session chair. To have the first talk, have 3 talks in this session. The first talk will be given by Sean Azzopardi. The title of his talk is Incorporating Monitors in Reactive Successes Without Paying the Price. Sean, please share your screen and go ahead. Thanks.
So can you hear me?
Yes.
Okay, great. So I'll start. Okay, great. So hello, my name is Sean Azzopardi from the University of Gothenburg. Today I'm presenting this work done in collaboration with Neil Peterman and Gerardo Schneider, also from the University of Gothenburg. This work is about incorporating monitors in reactive synthesis without having to pay the price of having to analyze the monitors and their properties in the usual way you have to do when considering as in reactive synthesis. So reactive synthesis is given an LTI specification over some input and output propositions. It gives us a set of techniques to produce a system that is able to control for these output propositions in a way that satisfies this formula when possible. When it is not possible, we say the formula is not realizable. Now, LDL has been used so this is very useful. It allows us to not program, which can introduce bugs, of course, but instead allows us to produce a system that automatically satisfies a certain specification. However, when LTL has been used in industry, we found that practitioners prefer extensions of LTL with some kind of operational aspects, such as regular expressions. For example, as used in ForcePreg. So this begs the question of if we consider such combinations of something like LTL with something operational like regular expressions or something like automata. How can we synthesize a controller for such specifications? So this is the problem we'll be considering here and at a very high level. And now let's look at an example of when doing something like this can be useful and having some kind of regular expression or automaton that triggers a certain LTL formula. So consider that we have something like a room, a kitchen, and a cleaning robot who must ensure this room is clean. We don't want the robot to be cleaning all the time, since that would be bothersome, it would get in people's way, but instead we wanted to do this in an intelligent manner and as sparsely as possible. So instead of having it run all the time, we want the obligation for the room to be clean to be triggered only in certain circumstances. We want it to be triggered if the room is dirty, essentially. It has been in use for example, n time steps. And after those n time steps, another m time steps have passed where it is not in use. So writing something like this in LTL is possible, even though it is more cleanly written as a regular expression, perhaps using lots of untils. We could write something like this, but when we consider it as part of an LTL specification, for example, in Strix, Strix is a reactive synthesis tool. It produces a controller that is very large, even for very small n and m. since it needs since it produces an enumeration of all the possible states of the produced strategy. But something like this, from a practitioner point of view, could be more nicely represented in maybe something like an automaton, something like irregular expression, and as you can see, this is not really related. This trigger condition is not really related to the obligation to ensure the cleaning. So if this is true or not, it doesn't really affect whether the robot can get the room clean or not, or the strategy it can take to ensure the room is clean or not. Just specifying the starting point of that obligation. So specifying, going into that detail for the specification used for reactive synthesis is not really needed. Another problem with this is how to express that this needs to happen repeatedly. So after the room has been cleaned, how do we restart the counting for the trigger condition? Perhaps we could do it in LTL by assuming something else out of the environment, by adding some new variables to the robot, but that only increases the size of the problem. And reactive synthesis is already 2x speed time, so we should not really do that. So in this, so my proposal here is that something like this a trigger like this can be extracted out of the specification, and instead we can have a monitor for it, as used in the runtime verification community. And we can focus the control synthesis on the actual obligation, on the ATL part. So we will have monitors that observe the environment, that detect when an obligation should come into, when an obligation comes into play, and then LTL to describe that obligation, LTL formula. So we will have two modalities. We will have a monitor that triggers the obligation, that triggers the LTL formula, and the obligation remains forever. Or the monitor triggers a co-safety LTL formula, and as we know, co-safety LTL formulas admit finite witnesses, so that when it is satisfied, we give back control to the monitor, and this triggering can repeat recurrently. So the problem we are considering here for these kinds of combinations is how to synthesize reactive controllers for these. And also, we don't want to pay the price. That is, we don't want to have to analyze fully the monitor when synthesizing this LTL formula. Let's look at this more formally. So for the first modality, for the simple trigger, we have that the monitor can trigger an LTL formula. For the repetition, we have that the monitor can trigger a co-safety LTL formula, and this can happen repeatedly. And we are also allowing some environment assumptions on this formula in the form of this implication. So yeah, something to note is that, of course, the monitor does not output. It is only monitors the environment propositions. And that's if the monitor does not trigger, then pi is trivially satisfied. Since if it does not trigger an obligation, then there are no obligations to satisfy, and we are okay. Semantically, over a trace, this simple trigger looks like this. So the monitor must hold over a finite prefix the execution trace, and from then on, phi must hold. And the repetition looks something like this, where the monitor, and so the monitor holds over a finite prefix, and then the co-safety formula must hold. When as we shall see how to determine this point later on, when a witness has been witnessed, the control is given back to the monitor. The monitor is restarted, and the process continues forever. And either continues in this way, or either the monitor just never matches. So there is no obligation that is triggered. So what are we going to use for monitors? We're going to use symbolic automata. Symbolic automata monitors are used in the runtime verification community to represent very rich properties. They have a set of internal variables. When these are, so in the monitoring community, sometimes these are infinite states variables, so something like real numbers or integers. So that makes them less amenable to something like to model checking and analysis in general. But here we make no choice on this. You can choose them to be finite state, you can choose them to be infinite state. We're just going to assume that these monitors are given, and we are going to trust that they're going to work as they're supposed to. We have a finite set of states, and we have a flagging state, a special state, which is essentially a finite state, but with a difference. And the transitions, we will have guarded commands. So a symbolic automaton looks like this. So this is encoding the property I mentioned before, the trigger property I mentioned before about checking that the room has been in use for n time steps. So here we have a guard over an environment proposition and the internal variable. So we are keeping a counter for how long the room has been in use for. When it has been in use for more than n time steps, we are going to start counting how long the room has been unused for. And when it has been unused for n time steps, we are going to reach the flagging state and trigger the obligation. So here we have guards, and then we have actions over the variable states. Actions when the guard is true, the transition is taken, and the action, the transformation on the internal variable valuation performed. Something else to note here is that when you reach the flag state or final state, the monitor stops, as in no other extension of that prefix is accepted. So we are only accepting at a single point of a given execution trace here. Okay, so these automata can be model checked to check if they do what you want them to do. Here we're going to assume that they work as they're supposed to. We're going to trust the user. So to determine the point, remember the diagrams from before, the point where the monitor matches, we're going to simply check that. We're going to simply check for the point where the flagging state has been reached, and we're going to trigger the obligation at that point. What is left is when to detect the point where the cause safety LTL formula gives control back to the monitor. So we need to determine when the cause safety formula kind of ends. Here, we call that cause safety formulas admit a finite witness. And here we're going to be choosing the minimal such informative witness, which we call a tight witness. So for example, if we have A and next B, then the trace AB will be a finite witness. So so note that this is the exact point that this trace is satisfied. So any continuation of this will satisfy this formula, and any prefix of it does not satisfy the formula, any strict prefix. If we have something like next true, then any finite trace of length 1 will satisfy it, would be a tight witness for it. But even though any continuation of the empty trace will satisfy it, we do not accept the empty trace here, but since we have next here, we are going to wait at least one step. If we have something like A until B, then a trace like this will also be a tight witness for it, since we are going to wait until B occurs. So we can define this simply as follows, where you check that the finite trace satisfies the LTL formula, and that no other prefix of it satisfies it. We're defining LTL satisfaction appropriately to take into account, for example, this case also being next true. So now we have ways to. So we have. So we know points where the monitor triggers, and we know the points where the LTL formula gives back control to the monitor. So we can discuss how to synthesize for these kinds of formulas. So we call the semantics of this operator. And we want to check that if there is a controller for this specification, where we can also have assumptions about the environment. Our approach here is simply to check that, to strip away the monitor, to check if this formula is realizable. And if it is realizable, we construct a controller C for it using the usual methods. Then the controller here for the full formula is simply to sequentially join M with C, which looks something like this. So if you have a monitor and the formula, we are constructing a controller for the formula on its own separately without analyzing the monitor. And we can simply just join the final transitions of M with the initial transitions of phi, since they share a time step. So that is quite simple. For the case of repetition, we need to do something else, since in general, these controllers do not have a final state. So here there should not be a final state, because the controllers we generate using reactive synthesis are meant to really run forever. So they operate over infinite traces, so they do not have final states. But here we require a final state, since we need to trigger at some point. And we need to incorporate that in the reactive synthesis algorithm. Here, we start by using the usual methods, producing a controller that has no final states for this expression, stripping away the monitor. We construct a deterministic finite state automaton that recognizing all the finite satisfying prefixes of this formula, and this construction is also exponential, that'll be exponential. And we can simply intersect the automaton constructed with the controller. And by identifying the final states in this DFA, in this intersection, we can set them as final states in this intersection. And that we recognize all the tight witnesses for this formula. And then we can simply join them in this fashion to produce a controller. So that will look something like this. So we have the transition, the joining of the final and initial transitions as before, and we need to simply redirect the final transitions of the controller, the LTL controller, to the monitor. And here we're also resetting the internal variables of M back to the initial values, so that we don't have any interaction between the previous controller and this one. Something to note here, as some of you may have noticed, is that approach. This approach, we're not considering the monitor at all in the synthesis algorithm. So, which can be problematic if we have no restrictions on what the LTL part can be. So, for example, if we have this kind of environment assumption, this approach does not work at all. So if we have an assumption that whenever A appears, then in the next 2 time steps B will occur, and we have a guarantee that in the next time step, that if B occurs in the next time step, then now I need to perform this, which is controllable, unlike B and A. Then if the A occurs before the monitor triggers, then I have no hope of satisfying this guarantee. But our algorithm will not notice this, and will not notice this kind of problem. So we need to limit, we identify the set of assumptions, a set of assumptions for which our approach works for. So where we do not need to do any kind of analysis of the monitor for synthesis. So we simply have propositions over the atom. We have, so that's alpha. We have beta is simple conjunctions conjunction and disjunction over the propositional language and allowing one level of next. And the gamma is what we allow as assumptions, essentially invariance over this beta, the occurrence of this propositional language and conjunctions of these. So we cannot write something like this in this language. So our approach is sound. When M cannot reach a flagging state or the LTL part of pi is realizable, then we can conclude that that the combination is also realizable. But what we cannot say is that if the monitor can flag, but the LTL part is not realizable, then pi is not realizable. Essentially, here the problem is that since M is restricting the kinds of prefixes that can appear before pi activates, essentially that can make pi realizable, since it is creating further restrictions on the environment that is not actually being encoded in the synthesis problem for pi. Here, the procedure remains doubly exponential. So it's in the same complexity class, and the synthesis of the type controllers is doubly exponential here. And something to note is that the monitor remains symbolic even when we combine it with the other controller, so that this monitor we can give it parameters, so that the and then from the example can remain symbolic rather than giving them certain values. So we can have solutions for a general for general parameters when they are only used on the monitor side, rather than having to synthesize controllers for each possible instance evaluation of the parameters. And instead, and this is useful because the monitors can be executed on the fly, and we don't need to explore every possible execution statically. So like the usual reactive synthesis tools do. So in conclusion, we have given a language that allows the user to model some parts of the specification already concretely, and what to specify declaratively. Essentially, the user is essentially giving part of the strategy already, and our job is to fill in the rest. This has been implemented in a tool which you can find here. It uses streaks for the LDL synthesis. Essentially, though we do not implement the algorithm for tight controllers, but instead we use a transformation of the code-safety LTL formula with some new output events that only trigger when the formula has reached when a tight witness has been witnessed, which can be exponential in our examples. This didn't create a problem, but it is this transformation is exponential in general. So we should implement the algorithm given. So in future, in present, we are considering to consider different combinations of these monitors and controllers, considering them in parallel. How to make this procedure more complete. That is we actually need to pay some price here. Here we try to avoid this, but we actually need to extract some kind of LTL assumptions from these monitors to refine the synthesis. And we are also considering other, maybe perhaps higher level procedure operators between these monitors and and LTL. So that's it. Thank you.
Thank you, Sean. Is there any questions from the audience? Okay, so So my first question is, since you have an implementation, right? Which kind of a case studies have you done?
So we have tried this on 2 case studies. So the case study I mentioned with the robot, which has a substantial amount of environment assumptions, and we also tested this on a. We also had a case study from Syntcom, where streaks failed on. So the case study was parameterized by some two variables, like as in 2 integers, and streaks failed for when they were bigger than 10, and by implementing part of the specification in these monitors, we avoided that, and we managed to get a controller for the general case quite easily.
Okay, thanks. So the second question is, so somehow, so if I understand correctly, so you only consider Q safety specifications, right? Q safety.
So when we have repetition, yes, because when we have repetition, we need to end at some point, right?
Yes, yes.
And if we have something globally do something, how can we? What points are we going to end to give back control to the monitor to? So for core safety properties, this was quite natural, the point at which control can be given back to the monitor. In other cases, it's not straightforward. It's subjective what you choose if you.
Okay, I see. So somehow repetition. So you choose specification safety properties, right?
Yes, for yeah. But if you don't have repetition, then you can choose any general LTL property.
Okay. So actually, so I'm wondering. I mean, for LTL synthesis, somehow, the environment. The assumption is that the environment can do anything, right? Somehow you have this assumption.
Yeah, you have these restrictions. You have some restrictions on the environment, but yeah, they can do anything as long as they respect these restrictions. This LTL formula.
Okay. But now you have this. You add this monitor for this triggering condition, right?
Yeah.
So do you think? I mean, for LTL synthesis, the scalability is a big. When you think this scalability issue can be elevated or not?
So here we're trying to help the scalability issue, because we're trying to encode part of the problem in a monitor rather than encoding it in LTL. So we're trying to avoid having to input it to the reactive synthesis. For some problems, this works because we can reduce the size of the specification given to the synthesis tool. But in other cases, we cannot really do this because the resulting reduced LTL formula still needs some knowledge about the monitor. We're investigating that right now in those cases.
Okay. Is there any questions? Then let's next speakers.
Great, thank you.
So our next speaker, Guillaume Dupont.
Yeah, Guillaume, yes.
Okay, thanks. So can you? So the title of his talk is event first behavior approximation. So Guillaume, please.
Yes.
And go ahead.
Yes. So I'm sharing my screen. Wait a second. I can't share my screen. I have a few issues of software. I'm sorry. All right, that's weird. I cannot share my screen properly. I don't know why.
Log in.
Sorry, what?
You can exit and log in again. Maybe.
Yeah, I tried that. Thank you. Okay, so I think it's a problem with my viewer. That's okay. We'll use another viewer. It won't be ideal, but it will be okay. Yes. Okay. Can you see it?
Yes. Thanks.
Okay. Yeah, sorry for this slight mishap. All right. So thank you very much for attending this presentation. My name is Guillaume. I am from Toulouse in France, where it is currently cold and dark. But I regularly visit the ATVA website to get a little bit of warmth from the Gold Coast. Anyway, I will be presenting my work regarding approximation and how we can use FNB refinement to encode approximation for continuous behavior. Right, so this is the outline of my presentation. I will start with a little bit of context. I will talk about FNB and how we can use it actually to model hybrid systems. We then talk about approximation on a theoretical point of view, and I will finish with a short application to case studies for two types of approximation I will detail later, and I will finish, of course, with a conclusion. So hybrid systems are systems that integrate discrete and continuous parts at the same level. Usually the discrete part is called the controller and the continuous part is called the plant. Sometimes we use this formalism to represent them. So this is called an hybrid automaton. It's basically an automaton with a differential equation in the places. So the automaton part represents the discrete part, and the differential equations represent the continuous part. So as you see, a plant is basically modeled using differential equations, which can actually be quite rich since there is not a lot of constraints on these differential equations. And when these dynamics are rich, it's actually quite hard to verify or to implement such systems. So in practice, system designers, when they have rich dynamics, they perform what they call an approximation to simplify dynamics, which is basically finding a simpler dynamics with the hope that those simpler dynamics and the rich dynamics are somewhat similar at some way. The problem is, as you may have guessed, that this approximation is not always very rigorous. It's sometimes, well, often done on paper, and in the end, it doesn't appear in the final model. Like approximation is performed a priori, meaning it is done before designing the system itself. But approximation is based on actual sound mathematics. So the question we can ask is, why can't we formalize approximation and maybe make it like a formal development operation associated with formal constraints that we can use to prove approximation and prove an approximate system. So just a word on the state of the art. As I said, we traditionally use hybrid automata to represent hybrid systems. It's a formalism by Wajid Valor. So this is quite a low-level type of models that is usually used for hybrid model checking. There also exists hybrid communicating sequential process based on CSP by OR. which is made by different code, and also continuous action systems. But this kind of modeling doesn't feature high-level operations such as the refinement, which is why we use them. There are also hybrid programs which has benefited from the work of Simon Linel and Sarah Luz with high-level operations for some kind of refinement, but this kind of refinement is on the proof side, not on the model side. So it's quite different. And also there exists FNB, work of continuous and hybrid system in FNB and also hybrid FNB. But as for now, there is no such work for of approximation for these tools. And as for approximation, it's actually very common in hybrid model checking because actual hybrid systems have complex dynamics. So a lot of hybrid model checkers use approximation and over approximation with so-called flow pipes to actually perform reachability analysis, for example, D over DT, SpaceX, and FlowStar. I would like also to note, but I will talk about that a little bit later. There is also a work by Girard and Papas in Verimag in Grenoble about preliminary approximation using approximate by simulation. So the goal is to demonstrate the existence of an approximate by simulation between systems and perform model checking on the C+ system and deduce properties on the more complex system. And also, I would like to point out that there are a lot of work around the controller annotation, so basically taking C program, annotating it with information about the system and improving it. But usually the approximation is already performed because this is an implemented controller. So there is no explicit formal approximation operation basically. All right, so let's talk a little bit about FNB, a little bit, don't worry. So FNB is a correct by construction event-based design formal method by Jean-Raymond Adrial, the inventor of B, which is its predecessor. In this formalism, we represent a system by a state, which is a set of variables, and a set of worded events. And each event is represented as a before-after predicate, or BAP, which is basically a predicate that links the value before the event with the value after the event. And any system can be associated with a number of invariants, which are basically predicates that must be true at all times on the system. And when you write a system in FNB, it is associated with proof obligations that are generated using the substitution calculus. And this proof obligation must be discharged or proved to ensure that the system is correct. And the semantics of an FNB machine or system is a transition system or a set of traces that represent every triggering of events, provided the event can be triggered and the invariant remains true. And FNB is quite notable in the fact that it supports a high-level operation called refinement, and refinement, when it is correct between two systems, ensure that the traces of the abstract system are simulated by the traces of the concrete system. And this is a very powerful tool because you don't have to prove the simulation of the traces, but only the simulation of the events, which is usually far easier. So FNB is fundamentally discrete. How can we use it to model continuous behavior? So just as I talk about the before-after predicate, which is for discrete variables, we can have something similar for continuous variables. So continuous variables are basically functions of time, like in a lot of semantics, for example, for hybrid automata. And just like with before-after predicate, we have continuous before-after predicate for continuous variables. And the continuous before predicate is this weird red operator, which it's actually inspired by the before-after predicate operator in FNB. And then what it says is that on the past, on 0t, the variable doesn't change, it remains the same. It's called past preservation. You cannot revoke the past by assignment. On tt primes, which we could call like the present and the future, the variable becomes such that the predicate is true, and also the variable remains in some kind of evolution domain, sometimes also called local invariant, which looks like the predicate that is below the places in the hybrid automata. So basically, yeah, XP becomes such that on TT primes, it abides by P and remains in H. And we have a slight shorthand for differential equations, since this is the traditional form of dynamics for hybrid systems. And this is XP becomes such that on TT prime, it is solution of equation E and remains in equation domain H. So on the side, technical note, all of this and more actually formalized and special FNB component that are called theories. Theories are basically libraries, like formal libraries that you can use throughout your models. But it's less relevant here. But so knowing that we can model discrete behavior in FNB, and knowing that we can model continuous behavior with FNB, thanks to the continuous before after predicate, we can actually model any kind of hybrid system using this kind of generic pattern, generic layout, which is very much inspired by hybrid automata. So basically, we have three variables, time t. We need explicit time, but it is mostly for proofs. We have xp, which is the continuous variable, which is for the continuous state. Xs, which is a discrete variable for the controller, basically the discrete state. We find here that xp is the continuous state is a function of time, at least defined on 0t. And we have also here a general formulation of the safety. So basically, we want that at any time between 0 and t, the variable remains in some set I, which is I for invariant. And we have two types of events, discrete events. Discrete because they change only the discrete state, and they can read the continuous state. So you have a quad on the continuous state and a change in the controller. For example, this is what we call a sensing, basically. And we have actuation events, which are continuous events, meaning that they change the behavior of the continuous state. So basically they are linked to a discrete state, kind of like how differential equations are linked to a mode in hybrid automata. And they perform a change on the continuous variable using, as you can see, the continuous before after predicate. All right. So just a little word about refinement. So discrete refinement is quite well known in FNB. Basically, what you can do is you can add new events, provided they do not change the variables in any way, and you can refine each event, provided they are not triggered more often than the abstract counterparts. So basically, this is called strengthening. But the basic idea of refinement is you can change the behavior as long as it remains compatible with the abstract behavior. So it's very well known for discrete, but what does it look like for continuous events? Because for continuous behavior, you cannot squeeze a new time interval between two time steps. It doesn't make any sense. You have to have a behavior that remains on the same time scale, especially because we use a dense time, so we cannot squeeze anything between events. So the idea is to say that if we have two continuous variables, xpa and xpc, xpa is refined by xpc if they have a similar value. So the idea, what is similar here? Similar means that basically their value are identical up to some observation map here called O. Which is a relation, so not a lot of assumption on this relation. Basically, we say that there is XPA and it is mapped to some set of points, XPC, and we can make the link through O. So this is, we write it under this shortened form. This is called the continuous gluing invariant. Gluing invariant because it glues the concrete state with the abstract state. So as a short example, for example, if you have an abstract machine with Cartesian coordinates, so x and y, and you have a concrete machine with polar coordinates, so rho and theta, the observation map links rho and theta with x and y, and x is basically rho cos theta, and y is rho sin theta. And as you see, basically, on a technical point of view, continuous refinement is basically data refinement. What you refine is the value of the variables. You do not use, you do not add events, and you do not add time intervals anyway. So yeah, if we see what it looks like, so on the left-hand side, I have an abstract machine. On the right-hand side, I have a concrete machine. On the left-hand side, I have my XPA abstract continuous variable. And on the right-hand side, I have the concrete one. Safety is XPA in IA and XPC in IC on the right. I have this gluing invariant here that makes a link between XPA and XPC. And basically, when I write this, I have to ensure correct refinement. I have three main proof obligations. The first one is that the green invariant must remain true on the whole run of the system, which is because the green invariant is actually an invariant. So formally, if it is true on 0t, then after every event, it shall be true on 0t prime. So whatever how the time progresses, it must remain true. I also have a program simulation, meaning that when my concrete event transforms XPC to XPC prime, so actually the behavior of XPC on TT prime must be compatible with the behavior of XPA on TT prime. This is simulation. And most importantly, because I will talk about it, I will come back to it, guard strengthening. So the concrete event cannot be triggered more often than the abstract event, which means that if XPC is in GC, if this guard of the event is true, then it must be that the abstract guard is true as well. So if XPC is in GC, then XPA must be in GA. Like you cannot have the guard that is true more often than the abstract guard. All right, so now that we are prepared, how can we formalize approximation? What does it have to do with refinement? And how can we use actually refinement to incorporate approximation as a high-level operation in LMB? So the general idea of refinement is that we want some kind of flexibility, some kind of headroom in the refinement. Right now, refinement is written with this set membership operator, which is basically exact, so to speak. We would like something that is less exact, still rigorous, of course, but with a little bit more headroom. And the idea is to relax set membership using the continuous gluing invariant. And instead of mapping points to a discrete set of points, we want to map each point to a set of balls instead. So basically, your abstract variables is mapped not to one point, but to this point plus a slight ball around it of diameter delta. And there is something quite interesting that arises from this situation, is that you can either map the abstract variable to the ball around the concrete variable, which we could call downward approximation, because you go from abstract to concrete, so it goes down. But you can also start with a ball, a set of variables, and refine it to something that is stricter, which we would call upward approximation, just because it's in the other direction, basically. I will talk more extensively about those two refinement operations. So how can we formalize approximation? We introduced two operators, two functions on set actually, called expansion and shrinking. So I put the formula here just for reference. Basically, the idea behind expansion is that you have a set and you construct a set that is bigger than this set, so that every point of the expansion is between 0 and delta of distance from this set. So this is basically the set plus a little hell around it of size delta. And shrinking is the exact dual. So it's a set that is smaller than S, so that every point of this set is at least a delta from the frontier. And like it doesn't cross out of the set, so it is strictly included and a delta from the frontier. And the idea is that expansion is some kind of relaxed inclusion. It's an inclusion that is less strong than regular inclusion, and that allows to have an inclusion that is with a little bit of headroom. And shrinking is, on the contrary, a strengthened inclusion, so it's a stricter inclusion because you get less points, basically. A funny fact, well, funny fact, not if you have to prove it, but S delta and E delta, so shrinking and expansion, they form a Galois connection. Basically, they are adjoint, if you want. They are dual in a very specific way, and this is actually what allows us to use it in the refinement, and makes it possible to use it in LMB. And on another side note, when delta is 0, expansion is actually the identity, and shrinking is also the identity. And basically what you get is a zero approximation is basically identity or equality, actually. So where do you use shrinking and expansion? When well, one of the first thing you can do with it is define the delta set membership, which is a relaxed version of set membership. Basically, we say that X is a delta in S if X is in the expansion of S. So basically, X is either in S or somewhere near S, provided it's less than delta from the border of S. There is a generalization for functions and relations. This is a kind of anecdotal, but this is to remain rigorous because we actually need it when we do approximate refinement. So the idea here is instead of having strict refinement, exact refinement, we have delta refinement here. And the only thing we change is that instead of set membership, we have delta set membership. There is a strong theorem here. So basically, one of the problems we have is that because it's not exact set membership, we have a few issues regarding substitution when doing proofs. So proofs cannot be done in a traditional way. But we have a weaker result, which is still a very interesting result that said that sufficient condition to deduce XA in PA when you have XC in PC is that the observation of PC is in the shrinking of PA, or that the expansion of the observation of PC is in PA. So basically what it says is that to prove this kind of formula where you need to prove XA in PA when you have XC in PC, which is called the predicate strengthening, a sufficient condition is to have PC more than included in PA, or well, no, less than included in PA, or observation of PC more than included in PA, basically including plus some headroom. So why is this of particular importance? Because this predicate strengthening, this shape of proof obligation, is actually found throughout the proofs pretty much everywhere in FNB. You may have guessed that it looks like a growth strengthening in particular. So how can we use it? So I took back the exact same example as before, but instead of having a continuous Green invariant, I have approximate continuous Green invariant. Yeah, we have this tiny delta here. The model remains basically the same instead, except for this particular Green invariant. But when we take a look at the proofs it generates this growth strengthening instead of the strict growth strengthening. So instead of exact set membership, you have delta set membership. And as I said, we cannot just make a substitution and reduce it and prove it easily. But thanks to this theorem I gave, we have actually a sufficient condition to guarantee that this is provable. So basically what this theorem serves here is to design the concrete guard in accordance with the abstract guard, or the abstract guard in accordance with the concrete guard to allow for easy proof of the guard strengthening. So basically, when you have the abstract guard, you can deduce the concrete guard, and when there is a concrete guard, you can deduce the abstract guard. And this is why I call it a pattern, because basically you give a few informations and you get other informations for free, and this allows you to perform the proof easy. Right. So yeah, basically having the abstract guard and obtaining the concrete guard, this looks like downward. Basically, you have the abstract system as a whole, and you can deduce the concrete system. So this is actually downward approximation. And in the other direction, this is an upward approximation. You have a target concrete guard, and you deduce the abstract guard you want to have so that you reach this target. So how can we use approximation on concrete case studies? First, downward approximation. Downward approximation is probably the most it's the most intuitive one. So a very famous case study is that of the inverted pendulum. So you have a mass which is tied to a rod that is tied to some kind of motor, and you want to balance it around the vertical axis. And if you take the differential equation for theta, You have those sin theta and cos theta, which are non-linearities. So basically, this differential equation is very hard to work with because it is non-linear. But there is a theorem in mathematics that says that when theta is reasonably small, you can substitute theta with sin theta with theta and cos theta with 1. And the differential equation, once linearized, is a little bit easier to work with because you don't have cos and sin. And if you do that, basically theta is approximately equals to this theta L, theta linearized. So this is where we're going to use approximate refinement. So the plan is to have as abstract variable theta with a complex differential equation, because we can actually prove results on the convex hull of this differential equation. But when we want to implement it, we cannot implement it in an efficient way, like integration schemas are not very good for that. So in the refinement, we approximate it, and this is closer to implementation. This will be easier to implement. And the only thing that we must take a look at and be mindful of is that we need to strengthen the invariant. So this is a direct application of the theorems I said before. We need that the invariant for theta L is strictly included with a delta overhead in the invariant for theta. So basically what we have is here on the left-hand side, the nonlinear pendulum panel here, with theta and the safety invariant, which is theta is below theta max. And on the right-hand side, we have the pendulum with theta L. Theta L is approximately equal to theta, so this is a continuous doing invariant. And you have here the invariant that is strengthened by delta. So basically, you can calculate this invariant using the shrinking I mentioned it before. Yes, and basically, if you have this shrinking, actually, it's the largest invariant that is still compatible with the system. So this is a good example of downward approximation. For upward approximation, actually, I'm going to use a case study from GL and Papas. I talked about it during the state of the art. So what they have is they have a robot, and the robot has a very complex controller because of it's using servo motors, and basically the implementation has to be complicated because you don't have a direct access to the servo motors. But what they proved is that this complex differential equation can be approximated with a much more simpler differential equation. So basically here if you have a differential equation of p position and v speed, and here you have a differential equation of only p. Basically you can approximate PEC, this position concrete, which is complicated, by this abstract position, which is much more simple. And the strategy here is that you start with the approximation because proof is very much easier to perform on it. And once you have a proof that your system is okay, you do the approximation and you obtain a system that abides by the invariant for free. You don't have to prove it again. This is the principle of refinement. And yes, and that has the actual complex dynamics. And so you use upward approximation, so approximation in reverse. Your target is actually the complex system. Your target is the exact invariant. And so the source, the abstraction, is this with an expansion of the invariant. So basically, you give it a bit of a point. All right, so yeah, just to finish. So basically, you have downward approximation when you start from the exact system and you go to the approximate system. Usually, the abstract is complex and close to reality, so it's a closed model. But the simpler is easier to implement. And you have upward approximation where this is the opposite. You start from the simpler, easier to verify system, and you go to the exact system, which is more complex but closer to implementations. And each of these actually have been addressed in the previous work if you want to look at it. So basically what we've done, we made approximation a formal and explicit high-level operation. We have two directions, downward, so to go from complex exact to approximated, and upward, which is the other direction, and plus application to case studies. We wrote a lot of approximation meta theorems, in particular these predicate strengthening theorems that actually really make proof easier. And also models are available on the website if you want to take a look. And as per perspective, I would like to tackle problems of what happens when delta varies. Right now, delta is a constant, but it could be a variable. I think this is also a possible start for discretization and floating points, because discretization is basically modulo zero crossing and Zeno problems. Discretization is basically approximation. The problem is finding delta and finding the correct way of using schemas. And also we could use model checkers and validation, like Simulink, to check constraints on delta, or even guess constraints on delta, to see which condition on delta is needed for the models to be feasible. So thank you very much for your attention. I hope I didn't talk too long. And if you have any question, please do not hesitate.
Thank you. Is there any questions? Okay. So, I mean, so
Yep.
that you mentioned this. Hi, sorry.
No problem.
Yeah, the network problem. Sorry. Okay. Yes. So my question is, that you mentioned this kind of floating point. Do you think that you can, suppose involve this this characterization into your former definition of this phenomenon?
Sorry, I didn't quite get that. I think the end of your sentence got cut. Hello? Yes? Yeah, I think, I don't know if you can hear me, but maybe you can write the question in the chat. I think it will be easier. I'm gonna stop sharing because I should. Yeah. So if you can hear me, just put the question. Yes, thank you. Do you think you can include discretization into your framework easily? Yes. So thank you for this question. This is the next big task in my research right now. So discretization is hard for two reasons. For the first reason is how do you verify that between two time steps nothing bad happens? So this is called the zero crossing problem. And also, discretization usually use integration schema, which are basically prone to errors, like they generate errors, like mathematical errors. And so approximation tackles with at least the second problem. So basically, you can ensure that provided you have the correct delta for approximation, you can approximate your system. So this is at least one problem taken care of. The problem is still zero crossing, which is a very hard problem. But I think there are good hopes of using approximation to tackle this problem as well. So it won't be easy though, but it can be done, I think, and this is my next big step, I think. You're welcome.
Yes.
Yeah, I think Jolene has a few problems of connections. Things were running late. I think we can go with the next speaker. I know the chair, so I'm sorry.
Yes, I think we lost Julian recently. So
Yeah, he's struggling with his connection.
how about we just go to the next one, third one. Is there the speakers ready for the presentation?
Yeah, I will just share my screen. Yeah, so welcome everybody. Today I will talk about the compositional synthesis of modular systems, and this is joint work with Bernd Finkbeiner. Well, today I will talk about distributed systems and in particular their synthesis problem. So we have given a system that consists of n processes and that might interact with each other and that also receive inputs from an environment. So we are given a system architecture, just describing our system, and a specification of the global system behavior, for instance, an LTL formula. And then our synthesis algorithm derives strategies, one for each of our processes, such that the parallel composition satisfies the global system behavior. This is a very interesting problem because we are able to describe the global system behavior and also the behavior of interactions between our processes while we receive individual strategies for our processes. In general, unfortunately, the distributed synthesis problem is undecidable. However, there exists a bounded version. So we have, as an additional input there, bounds on the sizes of our strategies, and then we only search for strategies up to these bounds. Well, internally, the search for such strategies is encoded into a constraint system, and the solution of this constraint system then directly defines our strategies. However, we always consider the parallel composition of all the strategies we are searching for in our constraint system to determine whether or not the parallel composition of them satisfies the global system behavior. And therefore, we have a state space explosion here. This is similar to the state space explosion in model checking, but it's kind of even worse because we do not only have this explosion in the state space of our model, but also in the search space of our underlying constraint solver. And so bounded distributed synthesis is just not scalable in practice. So in other related fields like verification, compositional approaches have been proven to be a key technique for scalable algorithms. That is, we want to break down the one big verification, or in this case, synthesis task, into smaller ones, several smaller ones in our individual processes. So for the distributed synthesis, this looks like this. So we break down this big one distributed synthesis problem into several synthesis problems for our individual processes. The naive way to do this is to just have n separate synthesis tasks and to require all our strategies to satisfy the global system behavior. But this fails on almost all benchmarks because a process can just rarely guarantee the satisfaction of the whole system behavior alone. And so our smaller synthesis tasks become unrealizable, and therefore we don't find a solution there. To overcome this problem, assume guarantee synthesis approaches have been introduced. Here the main idea is to have an assumption and a guarantee for every process. Then our process gives a guarantee on its strategy or on its behavior of its strategy. And in return, it may pose assumptions on the behavior of the other processes. And therefore, it is only required to satisfy this specification, also the whole system behavior specification, if the assumptions hold. Furthermore, we also have to ensure that our guarantees imply the assumptions such that we just cannot assume anything. Well, the key question in assume guarantee synthesis is now, how do we come up with these assumptions and guarantees? And there exists manual solutions. That is, the user is required to just produce the assumptions and give us as an input to our algorithm. However, this is undesirable because, well, we use synthesis to have a completely automatic push button method to get a solution. So we don't want to have user interaction there. Another approach is to have iterative solutions. That is, our processes, the first process poses an assumption on the behavior of the second process. The second process then tries to satisfy the specification as well as the assumption of the first process, and again poses an assumption on the behavior of the first process that it needs in order to satisfy the specification and the assumption. And so we have a negotiation loop there between our processes that iteratively refines our assumptions and guarantees until we find a valid assume guarantee contract. However, this loop might not terminate, and therefore these iterative solutions are incomplete. So today I will present you a third approach based on so-called certificates, which is on the one hand completely automatical, so we don't require user interaction, and on the other hand it is complete. So our algorithm is called certifying synthesis, and it is based on so-called certificates. From these certificates that are synthesized completely automatically in addition to the strategies, we build then our assumptions and guarantees for our assume guarantee contract. I will first present you certificates that are represented by LTL formulas. This is sound incomplete and very human readable, at least for people who can read LTL, but it's not that easy to incorporate the search for LTL certificates into existing synthesis tools. And moreover, LTL certificates can be non-deterministic, which might yield an exponential blow up in our algorithm because we need to determinize the certificate first before we can check whether or not a strategy or a process sticks to its own certificate. Therefore, I will present you a second representation of certificates as labeled transition systems, so-called guarantee transition systems. These guarantee transition systems are by construction deterministic, and so we avoid this blow up there. Furthermore, it's way more easy to incorporate the search for guarantee transition systems into existing tools. And this is exactly what I will present you after we have seen what certifying synthesis is, a practical approach for it. It is based on bounded synthesis, or it is the bounded synthesis approach, and therefore we have, again, bounds on the sizes of both our strategies and our certificates. And then we reduce the search for certificates and strategies into a sub-constraint solving problem. Well, let's first have a look at the main idea of certifying synthesis. As I already mentioned before, our assumptions and guarantees of the assume guarantee contract are built from certificates. So we synthesize a pool of certificates, one for each of our processes, and the guarantee is then exactly the certificate of the corresponding process. So our certificates exactly capture the behavior a process commits to. The assumption of a process is then just the conjunction of the certificates of all other processes. So it may assume that the other processes will not deviate from their guaranteed behavior. And by constructing the assumptions and guarantees in this way, we already satisfy by construction that our guarantees always assume the assumptions. So we get a sound approach here. Moreover, the certificates capture the interface between the processes in the sense that they directly capture which agreements the processes need to establish in order to find a compositional solution. As an example, consider a factory with two manufacturing robots, R1 and R2 here. and they drive on streets in the factory. They want to approach different machines, and there's a crossing that is used by both robots. R1 wants to approach the blue machine to the right here, while R2 wants to approach the green one. So clearly, we do not want to have a crash of our robots. We require that it should never be the case that both robots are at the crossing, which is denoted by at C1 and at C2, and that they both move forward in the next step, denoted by go1 and go2, because then we would have a crash in the middle of the crossing. Well, to prevent that our robots just stay there at the crossing and don't do anything anymore to prevent a crash, we also add that our robots need to cross the crossing eventually after arriving there. Well, and due to some safety regulations in our factory, the robots have to emit a warning signal in every step just to avoid accidents between humans and robots. Here you can see that the blue specifications, so that robot 1 will cross the crossing eventually, and that robot 1 outputs a warning signal, does not affect robot 2 at all. So it can be dropped from the specification robot 2 has to consider. Analogously, we can drop the green constraints from what robot 1 has to consider. The specification of having no crash, however, affects both robots, and so both robots need to have it in their local specification. There's clearly no solution with the naive compositional synthesis approach for this example, because our robots need to enter the crossing at some point in time after arriving there, but no matter when they do, the other robot could just crash into them. With certifying synthesis, in contrast, robot 2 could have the certificate to always give priority to R1 at crossings. And then a strategy for R1 that enters the crossing regardless of R2 satisfies R1's local specification. In return, R1 can then guarantee to not block the crossing. And then a strategy for R2 that just crosses the crossing after R1 did satisfies R2's local specification. Well, so let's have a look at LTL certificates. As the name already suggests, our certificates are modeled with LTL formulas. And then we require our strategy to satisfy the specification if the other certificates hold. And since our certificates are modeled with LTL formulas, we can just do this by having this implication in the local objective of our process. Furthermore, we have to ensure that our process sticks to its own certificate. And we can do this by just requiring our strategy to satisfy its certificate. As an example, consider our robots again, and an LTL certificate that states that robot R2 will give always priority to R1 at crossings, because here it is always the case that if R1 is at the crossing, R2 will not move forward in the next step. Then we can come up with this strategy for robot 1 that emits the warning signal in every step and always lets R1 move forward if R1 is at the crossing and never moves forward otherwise. Well, and indeed, this strategy satisfies the local objective of robot 1 as long as R2 sticks to its certificate. And note here that the certificate does not contain the warning signal at all. And this is due to the fact that the warning signal is not relevant for the interaction of our process, of our robots, because they only kind of interact and may have conflicts if they are at the crossing. The warning signal is completely irrelevant for this, and therefore it does not need to occur in our certificate. Well, an LTL certificate for R1 that says that R1 will not block the crossing could look like this. So we say always if R1 is at the crossing, it will move forward in the next step. And this is indeed satisfied by our strategy for R1. Then we can come up with a strategy for R2 that also always emits the warning signal and lets R2 only move forward if R1 is not at the crossing. And then this strategy satisfies also the objective of R2 if R1 sticks to its certificate, as long as we assume that our robots behave realistically in the sense that R1 is not at the crossing directly after crossing it. S2 also satisfies the certificate for R2, and therefore we have found a valid solution of certifying synthesis with LTL certificates. And indeed, the parallel composition of these strategies is just a strategy that emits both warning signals at every step, and that lets R1 move forward if R1 is at the crossing and lets R2 move forward otherwise. So we don't have a crash there. Both robots are able to cross the crossing and both robots emit the warning signal. So this satisfies our whole specification. Certifying synthesis with LTL certificates is sound and complete. So our solutions are guaranteed to be correct, and we always find solutions if there is a solution for the classical distributed synthesis problem. However, as already mentioned before, it's not that easy to synthesize LTL certificates, and we might have an exponential blow up in our algorithm due to non-determinism in our certificates. When representing our certificates with guaranteed transition systems, however, we enforce determinism. So our certificates are modeled with the label transition systems, and therefore we have to slightly adapt the requirements of certifying synthesis or their formulation. We now require that our strategy locally satisfies the specification with respect to the other guaranteed transition systems. What does that mean? Well, in classical satisfaction, we require our strategy to satisfy the specification for all input sequences. In local satisfaction, in contrast, we only require to satisfy the specification for all valid input sequences with respect to a set GI of guaranteed transition systems. Well, and throughout this talk, you can just assume that this set GI contains the guaranteed transition systems of all other processes. And then the sequence is valid with respect to GI, intuitively, if it can be produced by the guaranteed transition systems contained in GI. So our strategy intuitively then only has to satisfy the specification on sequences that can really occur if our processes interact. Furthermore, we have to encode that our strategy sticks to its own certificate. And since both strategies and certificates are now labeled modeled with label transition systems, we can do this with a simulation. So we require our guaranteed transition system to simulate our strategy. And therefore, every sequence that can be produced by our strategy will also be produced by our guarantee. As an example, consider again our robots and a guaranteed transition system for robot R2 that models our, it gives priority to our R1 certificate here. So in fact, robot R2 never moves forward if R1 is at the crossing and always moves forward otherwise. When we then have a look at the strategy for R1 that we already have seen before in the LTL certificates example, we see that S1 locally satisfies R1's objective with respect to G2. Note here again that our certificate does not say anything about the warning signal, because the warning signal is just irrelevant for the agreements our robots have to establish. We can then find the following certificate for R1, which is essentially the very same transition system as our strategy, but does not say anything about the warning signal. And because of that, also our simulation holds, because we only require the guaranteed transition system to simulate the strategy on outputs that are relevant for the communication of our robots. Well, having a look at the very same strategy for R2 as before, we can now see that also S2 locally satisfies R2's objective with respect to G1. And since S1 and G2 are again, S2 and G2 are the same transition systems, when we emit the warning signal, also the simulation holds here. And so this is a valid solution of certifying synthesis with guaranteed transition systems. And as you see here, we found a solution with the very same strategies as for LTL certificates. However, this is not always the case, because our LTL certificates can contain non-determinism and also liveness, while our guaranteed transition systems cannot. However, it is still sound and complete. That is, we will also always find a solution with guaranteed transition systems if there is one with classical distributed synthesis, although we might find different ones than with the LTL certificates. So let's now move on to how to practically synthesize assumptions and guarantees and our certificates from which they are built. So as already mentioned before, this is a bounded approach, and in fact, it's built up on bounded synthesis for single process systems. There, we have a specification for this single process and a size bound on the size of its strategy. And then we encode the search for such a strategy into a constraint system. This constraint system consists of several constraints. For instance, one that says that our transition system indeed represents a strategy, but the constraint that is most relevant for us today is the one that says that our strategy satisfies our specification on all input sequences. In our certifying bounded synthesis approach now, we build a constraint system that consists of n copies of this monolithic constraint system, one for each of our processes. Then we add variables that encode our guaranteed transition systems, and just to be able to search for them as well, so that the solution of our constraint system also defines our certificates. And then we have to encode the requirements of certifying synthesis into constraints. So we add constraints that ensure that our guaranteed transition systems simulate our strategies. Well, and furthermore, recall that we did not use classical satisfaction for certifying synthesis, but local satisfaction. So we also need to adapt this constraint. So there are a lot more technicalities involved in how to really encode these constraints, but I will not go into detail this. For this, I refer to the paper. Just note that we have connections between our constraints because we use local satisfaction. In local satisfaction, we already consider the guaranteed transition system of the other processes, and therefore our constraint systems are not completely separated because they use the same variables for our guaranteed transition systems. So we have one big constraint system for our certifying bounded synthesis and not n completely different small ones. However, we only have connections between our strategies and the certificates. Well, in classical distributed synthesis, we have connections between strategies and the other strategies. And in practice, it turns out that our guarantees are usually way smaller than our strategies, and therefore our approach does not suffer this big state space explosion as the classical algorithm does. Well, we have implemented a prototype of certifying bounded synthesis that is based on the monolithic bounded synthesis tool BOSI. And we compared it to an extension of BOSI to distributed systems that essentially just implements the distributed bounded synthesis algorithm. So here I will present you 5 of our benchmarks, where the first 4 stem from the synthesis competition. And we report on the running time in seconds for both of our tools as well. The timeout here was 60 minutes, so 1 hour. And we directly see that certifying synthesis clearly outperforms distributed BOSI on all instances. But let's have a little bit closer look at this. So here, the load balancer. Here we see that certifying synthesis outperforms distributed BOSI, but the advantage in terms of running time is not that big. So it's less than a second. And if we have a closer look at the solutions that we synthesize there, we see that we get large certificates in the sense that our processes need to know the full behavior of the other processes in order to find a solution. So our guarantees are of the very same size as our strategies. And therefore, the advantage of certifying synthesis lies solely in the little bit of specification decomposition we do here, because we still kind of have dependencies between the strategies and the guarantees, but the guarantees are of the same size as the other strategies. But still, this suffices to outperform the classical algorithm. For the other benchmarks, certifying synthesis outperforms the distributed BOSI algorithm much more. So we see here that a classical algorithm times out a lot after 1 hour, while we still find many solutions with certifying synthesis. And having a closer look at these benchmarks, we see that we have small certificates in the sense that our strategies are bigger than our guarantees. For the ripple carry adder, for instance, our processes just model the bits of the numbers we want to add. And therefore, a process only needs information about the carry bit of the previous process, while the sum bit is completely irrelevant. And therefore, the guarantee of our processes is smaller than strategy because it can abstract from the sum bit. And here we see that in these cases, certifying synthesis really strives. For instance, for the 3-area ledge, we see that distributed Bose is not able to produce a solution within 1 hour, while certifying synthesis synthesizes both strategies and certificates in less than a second. So certifying synthesis is really beneficial if there exist solutions with small certificates and therefore with a small interface between our processes. And if there do not exist such solutions, we also see that the overhead of synthesizing these additional certificates is not large. Well, to sum up, I've presented you certifying synthesis, which is a sound and completely automatical assumed guarantee synthesis algorithm for distributed systems. So it is built on so-called certificates. So we synthesize additional certificates for our processes. And from these, we can then construct the assumptions and guarantees for our assumed guarantee contract. This is not only completely automatical and sound and complete, it also enables modularity of our system, because our assumptions and guarantees, and therefore our certificates, build a contract between our processes. And once we have established this contract, so once we have synthesized our certificates, we can exchange individual strategies safely with new ones, for instance, when our requirements change, without needing to perform synthesis for the whole system again. Because as long as our new strategy still satisfies or gives the same guarantees as the previous one, we still know that the parallel composition of the strategies of our processes will satisfy the overall specification for the system. Moreover, certifying synthesis increases the understandability of both the system and the solution. And this is because our certificates encapsulate the interface between our processes and therefore in which situations they might interact and may conflict and which agreements they have to establish. So we get a better look at how our processes interact in our system. And moreover, the understandability of our solution is increased because we only need to consider our strategies with respect to the other guarantees. And the other guarantees abstract from irrelevant behavior for the process we are considering. In the classical algorithms, we would have to consider all strategies together and can't really see which parts of the behavior of the other processes is now relevant for our considered process and for the satisfaction of the specification. Well, I've presented you two representations of our certificates as LTL certificates, as LTL formulas, and as label transition systems. Both are sound and complete, but the solution with guarantee transition systems is easier to incorporate into synthesis tools, and we avoid an exponential blow-up due to determinization. So based on these guarantee transition systems, I've then presented you a practical approach for really practically synthesizing strategies and certificates, which is a bounded synthesis approach and reduces the search for strategies and certificates into a constraint solving problem. And our experimental evaluations show that certifying synthesis makes distributed synthesis feasible in the sense that we find a lot solutions for a lot more benchmarks in reasonable time than the classical algorithm did. And moreover, we see that certifying synthesis particularly strives if there exist solutions with small certificates and therefore small interfaces between our processes. So thanks a lot for your attention.
Thank you. Can you hear me now?
Yes.
Okay, thank you. Is there any question from our audience? Raise your hand if you want to ask a question. Okay. So I'm wondering who should give the certificates. So when you want to verify some, when you want to synthesize some system, so the user should give the certificates, right? Should write the certificates.
No, so in our approach, this is kind of our contribution that we don't have to, the user don't have to provide the certificates. We also synthesize them. So we don't only synthesize the solution in terms of our strategies, but we also automatically synthesize the certificates that we need for our solution.
Okay, so you mean that started from some specification for the global system, you also synthesize the certificates?
Yes, so we are just starting with a specification for the global system and an architecture of our system, and then we derive our strategies and our certificates completely automatically.
Okay, okay, thanks. So, yes, if there is no question, thanks. Thank you. Thank you for a nice talk. Yeah. So I think maybe Joe wants to say something about.
Can you guys hear me? Hello?
Yes, we can hear you.
Yeah, okay, so yeah, basically just thank you guys very much. It's been a fantastic week, and we've got some really good speakers and talks and also keynotes. So thank you very much for attending. I hope you enjoyed it. And this will conclude this year's ATVA. And next year's co-chairs right here. So Jilin would be one of the PC co-chairs of ATVA 2022. And we hope to see you there.
Okay, thank you. Yeah, see you next year in Beijing, hopefully.
See you next year.
Yeah.